Hi everyone, how are you? I hope you're doing well and you had a great time with your family and loved ones during the Easter break. So this is the first video clip for this week, week 14, and we're gonna go into the chapter 14, which is the stress and strain transformation. We're gonna focus on the transformation in this class. So I'm gonna upload the PowerPoint presentation that I'm gonna use during this video so that you can have these slides. So let me share my screen so um, we can look at the slide. Okay, so here is the slide that I'm gonna post it on the Blackboard. All right, so this new chapter, the title is Stress and Strain Transformation, and we're gonna focus on the stress transformation. So, I'm going to talk about a little more details and introduction and the reason why we study this chapter and this concept later on when we talk about the equations and so on, and we also solve the problem. But the main reason is this because as an engineer, we're always looking for the maximum value, maximum stress, and this concept can be used to figure out where and what are the maximum stresses with a certain degree of changes and so on. So, okay, let's look at this slide. Here you see that. So here we have a stress block we call the tensor, and this is a small chunk of whatever your body, and based on these three-dimensional coordinate system. So here we have x-axis, y-axis, and z-axis, and this is our reason. And we can create this stress block parallel and perpendicular to all these three dimensions, right? So for example, this plane is perpendicular to this vertical axis y. This plane is going to be the perpendicular to z-axis. This plane is going to be perpendicular to x-axis. And then we can think about all components, all possible components of stresses depending on the direction and based on this coordinate system. So first of all, we can think about these three actual stresses, normal stress, right? Perpendicular to each plane. And then we're going to call it as a sigma x, sigma y, sigma z. Sigma stands for the normal stress right here. And the tau stands for the shear stress. So these are the normal stress perpendicular to this plane, which is going to be, since this plane is perpendicular to the y-axis, it has a direction parallel to y-axis. So that's why we call it sigma y. Same story, sigma x, sigma z. And then we have other two components parallel to other two axes, z and x, right? On this plane, same thing here, parallel to y and z, and this is going to be y to y and x, right? So these are shearing stresses because the definition of shear stress, remember that the stress parallel to the surface, right? That's why we call these are shear stresses, while this is perpendicular, the 90-degree angle to the plane or the surface. That's why we call it normal stress or the actual stress. So we can name it as sigma x, y, z. Those are all normal components. Shearing stresses, here is the naming rule. So let's say here we have tau, and there are two subscript. The first one is depending on which plane you are at right now. So let's say this plane is perpendicular to x. So we're going to put x first for all the strain, the shear stresses on this surface. So that's why we have the tau x something here. So that's how we determine the first subscript here. The second one is coming from the direction. The component is parallel to which axis? In this case, we have two components, one parallel to y-axis, the other one parallel to z-axis. That's why we call x, y, which means this is on the surface perpendicular to x-axis and parallel to y-axis, and so on. So finally, we have tau xy, tau xz on this plane. On this plane, we have tau zy and zx because this plane is perpendicular to z. So the first subscript should be z. And depending on the axis, y and x, right? So zy and zx. The same thing for here. So we have a total of 1, 2, 3 normal stresses and 1, 2, 3, 4, 5, 6 shearing stresses. When I write down everything here, then it's going to be tau xy, tau xz, tau yx, tau yz, tau zy, tau zx. Now, we will talk about the transverse shear in chapter 12, that when we have a shear stresses like this, these two stresses should be equal to each other based on to satisfy the equilibrium. So that means the tau yx should be equal to tau xy. So we can eliminate one of these unknowns, right? Because these two numbers should be the same. Since tau xy and tau yx should be equal to each other, same thing here, yz and zy and zx and xz, those are all same each other. So that we will have ended up having a total of 6 unknown stresses. In other words, if you can identify these 6 components of stresses, you can define the state of stress for any component based on the coordinate system. Okay, so this is kind of a basic. Let's move on to the next page. Okay, let's move on. Here we go. Now, let's think about a situation that what if we change the coordinate system with a certain angle, okay, with some reason. I'm going to talk about that in a minute. So then what we can do is we can apply this exactly the same thing here. So let's say initially we had x, y, z coordinate system. Now, some reason we changed the angle from x-axis to x prime axis, and then automatically this y prime and z prime will be angled as well because we always maintain the 90-degree angle between x prime to y prime and y prime to z prime, right? Like we did for x, y, and y, z. Then we can think about another stress block. Looks like this, perpendicular and parallel to all these new axes, x prime, y prime, and z prime. And then we can list out all the stresses, sigma x prime, not here, sigma x prime, sigma y prime, sigma z prime. So these are 3 normal stresses based on new coordinate system, x prime, y prime, z prime axis. And then we will have sigma x prime, y prime, I mean the tau x prime, z prime, and then tau y prime, z prime. So these 6 is gonna be the all 6 components for this new stress block based on x prime, y prime, z prime axis. So we're gonna talk about how we can define and calculate these stresses based on the angle change, okay? So in this chapter, we'll concern ourselves with how the components of stress are transformed under a rotation of a coordinate system, okay? All right, so that's one of the main topic in this class. And earlier I mentioned that this is more generalized situation based on the 3 axes, x, y, z, or x prime, y prime, z prime, which is a 3D, right? But in this class, we'll mainly consider the problems of we call the plane stress. In plane stress, the state of stress in which 2 faces of the cubic element are free of stress. So let me go back to this example here, so that the planes, okay, so the plane stress situation is that we are having these 3 stresses like unknown, but the other 3, the sigma z, tau yz, and tau zx, will be equal to 0, which means, so let me go back to this original stress block. We're gonna say this the sigma z, okay? And then we have, so sigma x and y will be available tau xy, which is going to be same as tau yz, and then tau zx will be available, or the tau tau xz, okay? But tau yz and tau yz and, let's see, stop. So tau yz and tau zx will be equal to 0. So tau yz and tau zx, so these are two out of plane direction of the stresses. So let's say tau yz, this is gone, tau zx, this is gone, and the sigma z will be gone. So all the remaining stresses will be our unknowns. Then we're looking for those stresses while these three are going to be 0. And let's think about which kind of a case can be classified as the plane stress situation. So here we have two examples. One example of state of plane stress occurs in a thin plate subjected to forces acting in the mid-plane of the plate. So let's say here we have a plate and we have applied forces all here. And these forces are all applied on the in-plane direction, not out-of-plane direction. Out-of-plane direction means this way, okay? Then we can think about all the stresses are parallel or perpendicular to xy axis only, not about z axis. This is another example. The surface of whatever your structural element, and here we have a circular rod or circular kind of a cylinder type of the structural member, and we apply the forces here. And think about the stress block and the point of the stress at the surface, okay? Due to the external forces here, we will have, the stresses parallel and perpendicular to these or these two directions, but not about the perpendicular to that surface direction, okay? So we can simplify it as a plane stress condition. So from now on, we're gonna move on to the next, from now on, we're gonna just focus on the plane stress condition, okay? So let's talk about the transformation of the plane stress. Okay, so let's look at this figure. So here we have a two-dimensional plane, x and y, right? And let's say this is let's say we have this wedge type of the structural element, and we're gonna think about all the stresses and forces parallel and perpendicular to each plane. So these two planes are parallel and perpendicular to xy, right, axis. But this side is not directly parallel or perpendicular to xy plane. That's why we are defining another axis, which is perpendicular to this side plane, okay? That is going to be x prime axis. And parallel to this line, we define it as y prime, okay? Of course, we maintain the 90-degree angle between x prime and y prime. So, and then we apply all the possible stresses applying on these three surfaces. So here we have one surface here, another surface here, another surface in the bottom here. So first of all, since this is the plane stress condition, that means we're going to ignore the stresses along with the z-axis. Z-axis should be going this way, but we're going to ignore all those shear and actual normal stresses along with the z-axis. Then we will have only two stresses on each plane, each surface. So this is going to be, in this case, we express it as a force, and force is going to be the stress times the cross-sectional area, right? So let's say this side area is going to be delta A. then the bottom area is going to be delta A times sine theta, and the theta angle is the angle between x-axis to x prime axis. Okay, if this is theta, this is going to be theta as well. If this is theta, then this angle is going to be theta too. So if the area on this side is going to be delta A, using the cosine and sine, right? We can say that area along this bottom is going to be delta A times sine theta. Area along this vertical portion is going to be delta A times cosine theta. So those are going to be the cross-sectional area on each surface. So that area times each stress. So this is going to be sigma x prime, because the perpendicular to this surface, we define the axis as a sigma, the x prime. Okay, so the force is going to be sigma x prime, the normal component perpendicular to this surface, times the corresponding area delta A. And now this is going to be the shear stress on that plane, which is tau x prime y prime times the corresponding area, which is delta A. So this is going to be the shear force. Same thing for other two surfaces. We can define and put those the force quantity in terms of the stresses and the area. So I said the area is going to be delta A times sine theta for both components, because those are the stresses under this bottom surface, right? So on this bottom. And then corresponding stresses are tau xy, and this is sigma y, right? Based on the naming rule. So when you combine those two together, it's going to be the shear force, tau xy times delta A times sine theta. This is normal force, sigma y times delta A times sine theta. And do the same thing for these two components. It's going to be sigma x times the area, tau xy times the area. So when you define all these force components on three different surfaces and apply the equilibrium equations, some of all the forces and some of all the forces in two different axes. Now I apply the equilibrium equations based on the x prime axis and y prime axis. So this is going to be my positive direction, and this is going to be my positive direction for all the forces. So based on my positive signs, here we have x prime component, this is y prime component. All other four forces, we have to break it into x prime and y prime component like this. This is going to be x prime component of this shear force. This is going to be y component, because we have to break it into parallel and perpendicular components based on these new axes. Same thing for this force. So we will have the x, this is kind of confusing. So I'm going to use a different color. So for this force, here we have x prime component and then y prime component, right? This is x prime component, y prime component for this vector, and then x prime component and y prime component, something like that. So I'm not going to go over all the details of this derivation, but this is just a statics, right? You can break any force into the two components in a vector form, and you can do that. So we can list out all the forces based on the positive signs of each axis, right? And sum of all the forces along the x prime axis should be equal to 0, and same thing for y prime axis. And then we solve this first equation for sigma x prime, okay, by dividing this delta A for everything, because every term has a delta A. To solve it for sigma x prime for everything else, then you'll get this equation. And equation number 2, do the same thing for tau x prime y prime. So divided by delta A for everything, and solve it for tau x prime y prime. Everything goes to the other side. This is the equation. And then what we do know is that in the sine cosine trigonometry, we learned that, for example, 2 times sine theta, cosine theta, we can simplify it as sine 2 theta, right? And so on. So we can simplify this kind of complicated equation, two equations, into this format as this. So we do know that the sine 2 theta is equal to 2 times sine theta cosine theta. Cosine 2 theta is cosine square minus sine square. So that we can say the cosine theta square is going to be 1 plus cosine 2 theta divided by 2, and so on. So we can simplify the earlier equation here. For example, cosine square plus sine square is there. So we can combine these two together and then find out the simplified equations as this. This is for sigma x prime, and this is for tau x prime y prime. Okay, so these two equations are going to be used for the further calculations. So how can we use these equations to solve the example problem? All right, so, and by the way, these are two equations available in your textbook in page 625, 14-1 and 14-2. So let's solve the problem, example problem. Let's see. So here we have example problem. This is example 14.2 in your textbook. The question is this. Here we have a state of stress. This is plane stress condition. So all the normal stress and the shear stresses are given. So these are sigma y and these are sigma x. To satisfy the equilibrium, of course, these two values should be equal to each other. These two should be equal to each other as well. So this is going to be 50 megapascal. Sigma x is going to be 80 megapascal in magnitude. And you can see this will provide a compressive stress. So I can write down it as sigma x is equal to negative 80 megapascal. And this negative sign will represent the compressive stress, while the sigma y will be equal to positive 50 megapascal because that will provide a tensile stress. We also have a shear stresses. If we have a stress on this way, and this is sigma yx, and this is going to be sigma xy, and the magnitudes are the same, but the directions are going to be this way, okay? And here we have sigma xy and yx. So this tau, sorry. So this tau xy, the sign convention is this. I didn't talk about the sign convention, so let's talk about the sign convention for plane stress condition. All positive directions of normal stresses is kind of easy. When we apply the tensile stress, that's the positive direction. The positive direction of the shear stress is this. So when we have, this is sigma yx and this is sigma xy. So sigma xy goes to the upward and sigma yx goes to the right direction. That is kind of a pair. That's the positive direction of tau xy. This is positive direction of sigma y. This is positive direction of sigma x. When you have this pair, then you automatically will define the other two taus down there, and the magnitude, of course, should be equal to this tau xy. So negative direction of these taus and the sigmas, of course, these are the negative direction for sigma y. These are the negative direction for sigma x, and then opposite direction of these two pairs, like this. So that will automatically determine other two pair. The other two stresses. So this is going to negative direction of tau xy. This is tau sigma y and sigma x. So these are all negative. These are all positive. So these are the sign convention for this stress block. So based on this sign convention, we can easily say that this 50 megapascal will have a positive sign. 80 megapascal will have a negative sign. And tau, we know that the magnitude is given as 25 megapascal. So the tau xy will be equal to 25 megapascal. What about the sign? It is negative, right? So we have to put the negative sign based on the sign convention here. You have to be careful about these sign conventions because we're going to put not only just magnitude, but also with the signs, positive or negative, into the equation. And when you miss these signs, then your answer will be totally different. So the question is here, the state of plane stress at a point is presented on the element shown in this figure. I just draw it here. Determine the state of stress at this point on another element oriented 30-degree clockwise from the position shown. So what we're going to do is, this is the original state, but we're going to change the angle in the the clockwise 30 degrees. So it's going to be 30 degree in the clockwise direction like this. So originally we had x, y coordinate system. So I'm going to draw it here. This is the original coordinate system, x and y. Now we're going to change the coordinate into x prime, y prime axis with this angle. So this is going to be x prime, perpendicular to that. It's going to be y prime. So this is going to be 30 degree. Because of that, the angle is going to be 30 degree as well. And with this new coordinate system, originally we had a stress block like this, but now we have to have block looks like this, perpendicular and the parallel to x prime, y prime axis. And of course, these are going to be the new axial or normal stresses, and these are going to be new shear stresses based on these new coordinate systems. So this is going to be sigma x prime, it's going to be sigma y prime, and these is going to be tau x prime y prime. So the question is, what if we change the coordinate system based on from the original one, xy to x prime y prime with this 30-degree clockwise orientation change? What are going to be the normal stresses, sigma x prime, sigma y prime, and the shear stress, tau x prime, y prime? So the question is, what is sigma x prime? What is sigma y prime? And what is tau x prime, y prime? Okay, I didn't talk about this sigma y prime earlier, but we had an equation for sigma x prime. That equation looks like this after the derivation and simplification. Sigma x prime was equal to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 times cosine 2 theta plus tau xy sine 2 theta. So this is the first equation. The second equation for the tau is this, tau x prime y prime will be equal to negative sigma x minus sigma y over 2 times sine 2 theta plus tau xy cosine 2 theta. We do not have the specific equation for sigma y prime, but you can easily find out the sigma y prime because we do know the relationship between sigma x and sigma y. Sigma x and sigma y, we always have a 90-degree angle difference, which means instead of having this theta, when you plug in, I'm going to use a different color. So plug in theta to theta plus 90 degree, okay? Then when you substitute this theta plus 90 degree into this equation, that will give you the sigma y prime. So if you'd like to find out the sigma y prime, you can do that. Just substitute the tau, theta plus 90 degree angle instead of these theta. when you do that, what happens is this term is going to be exactly the same. This term now and this term will be affected by this theta, the angle change. When you substitute theta plus 90 into here, then what happened? The cosine of 2 times this, so it's going to be cosine of 2 theta plus 180 degree. And for sine, the same thing, sine of 2 theta plus 180 degree here. What happens is, remember the cosine and sine function? I'm going to erase this sign convention thing to make a room for the remaining explanation. Okay, you remember that the cosine sine function, sorry about my poor drawing here. So this is the sine function, and cosine function, I'm going to use a different color. So cosine function looks like this. Okay, so instead of having just theta, substitute theta plus 90 so that we have 2 theta plus 180. That means from 2 theta to 2 theta plus 180. So we have a 180 degree phase difference, which means for the sine function, when you're here, it is going to be moved to this point, which is going to be exactly the same. When you're for your cosine function, then from here to here, right? So when we have a positive 1, it will become negative 1, right? So when you and even for the sine function, like let's say here positive 1 to negative 1. So when you're 0, it's going to be 0 as well, like cosine function as well. But when you have the value that will flip the sign from positive to negative when we have a 180 degree phase difference. With that saying, our sigma y equation, a sigma y prime equation, we didn't derive it, but you can easily say that this is going to be exactly the same thing for the first term, sigma x plus sigma y divided by 2. And now, because of this 180 phase difference, this sign goes to negative. Sigma x minus sigma y over 2 times cosine 2 theta. And then this one goes to negative as well, minus tau xy sine 2 theta. So that's how we can calculate sigma x prime, sigma y prime, and tau x prime, y prime. All right, so let's just calculate those. I'm going to erase this bottom portion. And then, I'm erasing the equation. So I'm going to rewrite the equation again. Okay, so let's calculate the new normal and the shear stresses. So the sigma x prime, the equation is sigma x plus sigma y divided by 2 plus sigma x minus sigma y over 2 cosine 2 theta plus tau xy sine 2 theta. So here the theta is going to be the theta is going to be the negative 30 because we are following the sign convention. So when we go around the counterclockwise direction of rotation, that is a positive direction. So clockwise 30 degree, theta will become negative 30 degree. So we'll just plug in all these numbers into the equation. Sigma x, negative 80 megapascal. Sigma y, positive 50 megapascal. Tau xy is going to be negative 25 megapascal here. And for theta, it's going to be negative 30. To do that, your sigma x prime will become negative 80 plus sigma y plus 50 over 2 plus negative 80 plus and minus is going to be minus 50 over 2. Cosine of 2 times negative 30 is going to be negative 60 plus tau xy, which is negative 25 megapascal, times sine 2 theta, 2 times negative 30 is going to be negative 60 degree. And when you calculate it, I got negative 25.8 megapascal. So this is going to be sigma x prime. So when we change the angle and the coordinate system from xy to x prime, y prime, like this, so this is x prime, y prime with a 30-degree angle change, then our stress block looks something like this, and this is going to be sigma x. So here we have negative value, so we're going to be compressive stress, 25.8 megapascal goes there. Okay, and when you calculate sigma y prime, you will get negative 4.15 megapascal. Using the second equation, you can calculate sigma x, the tau x prime y prime. All the details are available in your solution. Tau x prime y prime, you will get negative 68.8 megapascal. So with using these values, we can draw a state of stress for the new coordinate system. So we have sigma y of 4.15 in the negative directions, go this way. And then tau x prime y prime, we have a negative sign. So based on the sign convention, it's going to be this way. The magnitude is going to be 68.8 megapascal. So that's how we can solve the problem. All right, so in the next, this is the end of the first video clip. In the next video clip, I'm going to show you how we can use these equations and why we need to change the angles and why I need to understand how to calculate these stresses with the different angle changes. The main reason is because we are looking for the maximum point, maximum stresses, and we'd like to know which angle will produce the maximum stresses and what are those maximum stresses we call the principal stresses. So we're going to talk about those, and in the second video clip, and then in the third video clip, we're going to talk about now a little different way, the graphical method we call the Mohr circle. To develop the Mohr circle, we can easily do this transformation of the stresses with the different angles. Okay, so enjoy your study, and then let's see on to the second video clip later. Bye. Oops.